Hi, this is Mrs. Vrobel. This is Chapter 12, States of Matter, Part 3. So in the previous slides, we were looking at gases. We're looking at effusion, diffusion, pressure, Dalton's law, partial pressure. Now we're going to look at liquids. And just like we talked about kinetic molecular theory of gases, we could talk about kinetic molecular theory of liquids. So I have a bottle of my soda stream, and when you look at a liquid is very different from a gas. You could probably see some of the gas bubbles that are in my soda stream right now. They obviously behave differently than a liquid does, and the question is why? Well, please remember when we're talking about liquids, we're talking about clusters of particles. So these are molecules, and these molecules are weakly bonded to each other. So I don't want to say they're magnetic, but they're attracted to each other. And when they're attracted to each other, they're weakly attracted to each other. However, they're free enough to kind of swim past each other. And because of that, there's a couple properties with liquids. We know that liquids have definite volume. I filled this up to a liter, and it's going to stay a liter as long as it remains a liquid. And also, because these molecules can slide past each other, I move the bottle around, and obviously as I move the bottle around, the shape of the liquid changes. Whereas with solids, that's completely different, and we'll talk about that eventually. So looking at water, it's a great example of figuring out why do we see liquid water. Notice that there's a couple different things going on with water. So here we have oxygen bonded to hydrogen, and these are actual chemical bonds. But notice this series of dots here. So these are two separate molecules, and they actually have a weak attractive force, and we call this intermolecular. So intermolecular means between two molecules. So in pure liquids, we have what we call a dipole-dipole attraction. We also have what we call London dispersion forces, and we're going to talk about both here. So with a dipole you have to have a difference between the two atoms. So we're talking about chemical bonds, and one has a stronger attraction for electrons. So an example of this would be oxygen. Oxygen tends to have a stronger attraction of electrons on one side of a chemical bond, as opposed to hydrogen, which weakly attracts electrons. So what happens is in a water molecule, the hydrogen end has a positive or weakly positive charge, and oxygen has a weakly negative charge. Because of that, it's sort of like not quite a magnet, but the charges, they arrange themselves so that the opposite charge of one molecule is attracted to a opposite charge of another molecule. And we call this dipole-dipole attraction. So here we have a series of molecules, and what they've done essentially is they've rearranged themselves so that if you notice there's a pattern going on here. So anything that is positive is going to be right up against negative charges. And the same thing happens with the next molecule and the next molecule. So they line themselves up so that they're directly next to an opposite charge. So here we have water. Water has two hydrogen atoms, and notice they both have a weakly positive charge. And oxygen, because it's got lone pair of electrons, it has a stronger opposite charge. And this is what caused the intermolecular force, or the dipole-dipole force. Now, we actually give these type of interactions a name. And you have to live with the misnomer. It could have been labeled better, but because people started using this in their explanation of intermolecular forces, you're kind of stuck with it. It is not a actual chemical bond. This is just a very strong dipole-dipole attraction. So be very careful when you're talking about hydrogen bond. You're not talking about a chemical bond. You're just talking about an attraction. There has to be unshared pair of electrons on an atom, and that typically is oxygen, not always. And in order to have a hydrogen bond, you have to have one of the following: oxygen, nitrogen, or fluorine. So typically it's hydrogen with either oxygen, nitrogen, or fluorine, and they have to have unshared pair of electrons to have this attraction between each other. And what does this mean? Well, the interesting thing is, notice how water, its boiling point is 100 C, and we are so fortunate that water has a very high boiling point because life would not exist without this property. People have been combing the solar system for evidence of water, and they've found a great number of sites, different planets, different moons that have water, and their hope is that they're actually going to find life, for instance, on Mars. And because water has this special level of attraction, it has a high boiling point, it sustains life because of that. Notice that it drops significantly when we look at hydrogen sulfide, hydrogen selenide, and hydrogen telluride. So there's not as great of an attraction of these three with themselves, whereas water has a very strong attraction with itself. So here's another diagram of hydrogen bonding. Once again, notice the oxygen rotates itself so that it is exposed to two other hydrogens from two other water molecules. So like I said before, hydrogen and oxygen together, they develop a dipole, and within this dipole you have a very strong attraction of one water molecule with another, whereas these three elements you do not have as high of an attraction.